Welcome everyone to the online 1 week refresher course in DTC transformation. This is Prakash Ramchandran, and on behalf of EOTF and Ramanujan College, along with the uh, Ministry of Education, uh, Telecom Skillset uh, Council, and Magma India, I am uh, presenting here the DTC transformation uh, for the uh, Pandit Madan Mohan Malviya National Mission on Training and Teaching for February 22. This is day 3. The topic is 5G, and my background, I have been in the industry, ICT, including telco, 5G, working for basically AT&T and previously with Huawei and Dell, and currently the uh, organizer secretary for the EOTF. So my background is I have done couple of presentation in 5G for the last PMM NMTT 2021. This is for 2022. So I'm just going to go ahead with what we did was on the 5G core Magma, and followed up with data communication and 5G radio stuff. So here we will be covering the 5G from the perspective of the deployment, architecture to deployment. So going ahead, uh, what I'm planning is to make sure that we have end-to-end architecture and how do we proceed to the deployment. So the big picture, I will go through these 12 points. First one is 5G end-to-end network. How is the 5G solution provided by vendors and various content and the modules? What are the bands of frequency and the ranges? What is the radio coverage versus the capacity? What are the radio front, mid, and back hauls? And what are the typical service provider 5G products and solutions? And basically, we are looking at 5G new radio product specs and standards and how it is typically tested by the service provider. And I'll go with the case study of Intel FlexRAN to elaborate a little bit more deep dive into the technology, and then the associated real-time optimization that are desirable for the field to be able to use it effectively. And then finally, I will go with the enterprise 5G and what is India's contribution to 5G uh, for the IMT 2020, related to the modulation and for the rural deployments, etc. Under the TSDSI, which has been very active in trying to collaborate and bring together a effort from Indian side. With that, let me dig into the first slide. What is 5G end-to-end network? So if you talk about 5G end-to network, we do have to start with the uh, client device, which is user equipment, we call it, our mobile terminal as it was in 3G. And this has got a radio which can be from the 2G to 5G. You can use a tablet, even you can use a Wi-Fi for the access, or you can do remote desktop through the cloud. So whatever is the client that has to talk to the radio network. Now radio, if it is a Wi-Fi RAN, then it is a separate track. And if it is a LTE RAN, then it's a different thing. If it is a 5G new radio access network, that's different. But overall, we have to look at it as a converged RAN. So a 5G client or a 4G client talks to the network through the radio access network, which is obviously configured by some entity outside of it, which is could be a access gateway or something. Example we saw in Magma. Then this interface talks to the uh, core. Now, when it talks to the core, which is now in this case, it could be a 4G core or a 5G core, look for what is the service the UE is trying to consume. So if the UE is trying to consume a data service or a voice service or a SMS service. Obviously, it has to go through some of the, if it is a voice, it may be a SIP function, or if it is, it could be a voice over 5G, and it could be a user plane function for uh, getting the data, and then it could be some slicing function, network function for slicing, which could be for a EMBB, that is extreme mobile broadband, or it could be for narrowband IoT. So there are network functions, one, two, three, and each one composed of various functions like VNF123, CNF123. It could be a VM, or it could be a container, and all these are riding over or running over a runtime of network uh, function infrastructure. So the unified network uh, function is what we are looking, unified network function infrastructure over which the network function runs, and it is interoperable. That means anyone can talk to anyone and be able to provide the services which are ultimately the data, voice, SMS, or what kind of whatever kind of services, digital uh, experience you need, that has to be provided. Now this can be done either through the local edge computing cloud or MEC, or could be a traveling edge. Example, if it is a car driving and it has got a data center type compute facility and communication facility, but all of them run over the common NFVI infrastructure. That's the uh, objective, and that is a unified NFVI is there, and obviously the central cloud which is there at the data network on the behind the core, that could also be a distant cloud. So where the service is offered from depends on how the policies are uh, um, policies are uh, affected, and those which are end-to-end service is offered to the consumer by the provider. So provider has to provide in the provider network the facility and the capability to deliver the consumer the necessary service based on the various stacks that are involved. So the focus is on converged RAN with a network function which is interoperable, and at the 5G core. At the same time, we have a unified NFVI. So that's the uh, scheme of things we expect from a 5G end-to-end network. So the objective of the 5G architecture to deployment, the architectures are there in our, you have SA, uh, non-standard access, and SA standard access, and all that with the 5G new radio, and with through 4G or through 5G direct native. So depending on that, the what is the expectation with respect to what is currently in the 4G LTE through the evolved packet core? Instead of that, what? So we require enhanced network architecture for better QoS and SLA. It could be throughput increase, could be uh, what you call optimizing the latency, and reducing the capex, reducing the opex, improving the ARPU, so that sustainability of the uh, provider, and they have enough margin to cover for the built up of the new uh, network is what is expected. So 5G architecture to deployment in any region, any country, including India, is that it has to satisfy these five requirement to be able to make it what you call profit making, at least to sustain the operation. So it should not be expensive, it should be cost optimized, which is the first criteria as far as third world countries and developing countries are there. Given that, let's look at a commercial 5G solution. So commercial 5G new radio solution, if you look at, if we take a example, Radisys, which is bought over by Geo, or it could be Bharti Airtel having some provider, some vendor working with them, like could be Ericsson, Nokia, etc. So what we are looking at is there is a UE stack, there is a RAN, so there is a UE stack, RAN stack, and core network. So UE stack is, we'll talk about it. RAN stack can be a 4G or it could be 5G. So it could be ENB non-standard architecture to be able to use the existing 4G and working with ENB and GNB. So ENB and GNB are nothing but the base station transceivers, which is, you can call it as uh, a 5G and 4G to 5G migration radio. And they are because of the different frequencies and all, we'll see that. And on the core side, you can have a APC, which is the 4G core, or you can have a 5G core network. So there are multiple combination, and how does one go about it? This is based all on the release 15, 16, 17, and into the 18. So working items are going on, and we know that IMT 2000 got us something reasonably good to deploy. So the commercial 5G solutions, typical 5G NR product specs, if you look at it, you'll find that there is a, if I point to the UE has a L2, L3 protocol software. It has got L1 abstracted with MAC to MAC and uh, FAPI, which is like an interface for the dual connectivity, etc., and cellular, that is for the microcell, etc. Then you got the L2, L3 NAS is the it's the access stratum, network access stratum API, which was defined in 3GPP release 15. So the products obviously are going to be behind because specifications go ahead, but the products have to catch up with that. So you find that UE today we are getting UEs which are in 5G bands as well as 4G and 5G dual band and dual connectivity to be able to operate with both the 4G and the 5G backhauls or 5G cores. So if you look at the core, the UE talks through the core. If it is a new 5G core network, then you have the access management, session management, and user plane function, and they comply to the at least minimum 3GPP release 15. And then you also have the 4G core, which is already available as EPC, and then we go to the intermediate part, which is the GNB or the radio part. So if you have 5G new radio, the GNB is the name of that. Instead of E node B, it is G node B, and it has got the uh, the BBU, basically baseband unit, is split into three parts: CU, DU, and RU. So that is the central unit, distributed unit, and the radio unit. The radio unit is the one which is the one in the cell towers, etc., or below that, where it can operate on the radio remote head and with the signals that are there processing it. So you have got the central unit, which is control plane, central unit is user plane, or the combination of the two. And then you got the distributed unit distributed across, which is the architecture, new architecture for a distributed, disaggregated architecture. And then, of course, deployment model. If you are using a backend of 4G core with a new radio, then it is a non-standard access. And if it is a deployment mode, is say it is pure, basically everything is 5G from new radio to the back 5G core network. So these are the modes, and then it can be in the sub 6 gigahertz, which is we will discuss about it. So basically, the band or the carrier frequency is in that range. You can also have millimeter wave, which is in the millimeter wave front, which is in the 24 gigahertz range. So a product typically has specs for the UE, either for the EPC or the 5G core network on the core side of it. On the radio side, GNB is split into various modules, and this is what you need to be able to upgrade this to be able to operate if you are going with the NSA model. So band frequency ranges, there are two specific mention: frequency range 1 and frequency range 2, called FR1, FR2. The 4G used to operate in 900, 800 megahertz mostly, and the speed, throughput, etc., were in the 10 to 100 Mbps, and latency was of the order of 20 millisecond plus, and you could have a coverage of 4G radio over 1 to 2 kilometer, and the mobility obviously was able to do intercell. Now with the 5G FR1, which is the frequency range 1, is under 6 gigahertz. It could be 3.2, 5.4, or whatever those which are allocated by the ITU or the Wireless Radio Council, WRC, to the nations. Each nation applies there. And obviously, India has its own allocation, and it is trying to allocate those spectrum, the license spectrum, to the providers like Jio and Vodafone and Bharti Airtel, which are the primary ones here, with the BSNL being another one, which is still focused on 4G. So given that you have got this 100 megabits per second to 1 gigabits per second speed or throughput, with the 5G FR1 you can go uh, 2 to 10 millisecond latency range, and it can cover about a kilometer, and at the same time it can also do the intercell mobility. Now if you look at between the 4G and 5G, the average 15% improvement is what you get overall in the under sub 60. But if you really want to gain on the higher side, then you must go to the FR2, which is the millimeter wave, which is in the 24 gigahertz to 54 megahertz gigahertz. And then in that gigahertz you can get a speed throughput of 1 gigabits per second to 4 gigabits per second. Now we are talking of average and peak. We are not talking sorry, we are talking of average and statistical average, and peaks obviously can be higher, but focus is here that on the 5G FR2 you can get a better latency, that is 1 to 5 millisecond, and you have 100 to 200 meter coverage. Of course it has narrowed down from 1 kilometer, so only 1/10 coverage can be got with a higher 10 times this speed, and that you have to give to that. And obviously it is inter microcell, so you need microcells for denser deployment because the range is lower. So 1 kilometer, if we have coverage, you can see it is 100 meters. So obviously at least 10 times, even without doing any detailed calculation, we can say that you are going to have a lot of, instead of 1,000, you are going to have 100,000 cells in a square kilometer type. So that's the scale we see. And if you go to the 5G advanced, which is the includes the C band and K band, which are 2 to 4, 4 to 8. Uh, there are some interlap, overlap, and that's why you will find complaints coming. And all this will be once the frequency bands are vacated properly through uh, the government's participation, whether it's FCC or if it's a TRI in India, all this will happen at some point of time, and then sooner we'll get the ability to go from 5 to 5G, 5G to 5G advanced, and there you are expecting a latency of 1 to 2 millisecond and 100-meter range, and not 100 multiple hundreds, but just 100-meter. And so obviously intermicrocell mobility has to be attained here. So this gives you the band frequency range and the spectrum and spectrum allocation aspects of it, and technical terms. Uh, Financial, I leave it to the market. So we have here sub 6 gigahertz radio cell, and obviously the you can see the number of users. I mean the concurrent users. This is statistical. Actually, it can over a day you can have many thousands and thousands. But given the power requirement, femtocell are generally inside, and indoor outdoor microcells. Picocells are also used to certain extent, but the sweet spot for 5G is the microcell, like sweet spot for 4G was macrocell. So you are going to see a spread of microcells versus what was there in the macrocell, which becomes our aggregator for all these microcells. And that's how it is going to happen. And there are some tables I have put on the right side to see that you also have some frequency understanding, because obvious requirement is that you have a band, and your band is nothing but carrier plus minus whatever the side band is there. So that has to be not mixing with each other and interference. So basically cross layer interference should be minimized, and that's the key for. So you can see users, locations, whether indoor, outdoor, the higher frequencies in the millimeter wave really are attenuating, basically our cross interference is there. Therefore, the dB level that is necessary is not attainable for huge distances. So that's the reason that micros uh, will require more. Uh, it has a less coverage, and but capacity wise it is able to manage, whereas best 4G is what is required. So it's a combination of 4G, 5G, pico, femto, all kinds of cells we'll have to do to enable 5G. Now going to the Um, uh, Next one. So you can see the typical telco in India obviously has a AMF, access management function, session management, and user plan function available to them through open source as well as through hardening what they have done there in their own stacks. But the other parts of the end-to-end 5G network solution requires UE, the G Node B, the radio 5G radio, new radio, and then connecting through access management or the access gateways. They should be able to have a session created for the tunneling to create a user plane function through user plane function to be able to cover the cell range or the region or whatever may be the geographical distribution. And then obviously you need to connect to a data network, and data network could be at the breakout in the edge, or it could be in the beyond the core in the cloud, which is a longer distance with higher latency. But essentially, they need to have additional functions like application function running in those data networks, and it could be a SIP, it could be IMS, it could be any of these applications which they provide media application or anything. And then you need a packet charging function so that your policy based you can apply the subscriber database, which is user data manager, user data management, and that is the subscriber, and subscriber database has to be there. And then your authentication functions, and then you have got the network slicing function. So this is a typical modular approach which needs to be done, and most of the people have their AMF, SMS, UPF, whether it is open source or their own, and other thing they are trying to integrate either with the legacy or with the new modules for each of them, and each of these need to be developed and deployed. And vendors are there, plus the service providers are there. There is a, it's more open for usage. So if I look at one of the uh, new radio control plane stack, it can be with or without even split. So there are some interfaces which have come up in the industry because of the either ORAN or Open RAN, and you will find that there is a uh, split in the GNB. So basically, if you have a baseband unit and that happens to be 4G, that used to be a not disaggregated, it was together. But now you are disaggregating into the CU, DU, RU, as well as you are looking at the layers of the packet transfer with layer 1, layer 2, layer 3. So the VNFs which are there, which are created, that is virtual network function to run on the network function infrastructure, they need to support some of these interfaces so that they become interchangeable through vendors. One vendor can provide you the CU, that can provide the DU, and then so mix and match. You can do the best of the breed you can take. So for all that, you need to have a. If you look at the stack here, the GNB, you can see there is a central unit, and central unit application has a stack with the radio resource control, the packet data control protocol, you have the F1AP, and then you have got SCTP, which is the secure transport control transport protocol over IP. So usually SCTP is able to connect the DU, that is the distributed unit, which is across various cells, macro cells, I can say. Then you can connect that to the CU, and then CU central unit has what you call interface, which goes and connects to the what you call the application. It has got the manager for the GNB. It has got the UE connectivity manager. It has got the resource manager, and so all of these again go back to the core, and then that's how they connect through E1 in this case. So F1 is in the front hall, E1 is the between the within the CU. CU is all whether it's a user or control plane or whatever it has got, they connect. So let me take you to the next diagram, which will show that you got a new radio control plane stack architecture. Here we have even split, even interface is split. That means what? The CP and the UP of the central unit can interact with each other separately besides the DU in front can deal with the SCP, SCTP or IP stack for connectivity. So DU deals with the CU through SCTP or IP, whereas CU deals with its own CP and UP through even split. So these are some of the interfaces E1 and F1. They are very critical, are the most important ones for radio and the ability to manage the front hall, mid hall, and the back hall. So let's look at the CU DU solution architecture here. It's more, a little bit more deeper into it. So you got the DU. You can see multiple DU units are there stacked together. They could be in a different nodes, and those cells, each one has obviously multiple cells, usually three sectors, and so it could be 3, 5, 7, depending on how the deployment is. But three cell is very common, and then if you have angle of something like, let's say 90 to 100 degree, you can cover 270 or you can cover 360-degree, depending on how it is angular, how the antennas are installed and all that. So DU faces with the RU, so it antennas feed the data to the F1 interface for the user plane, and also to the control plane, F1C, for the DU. So what feeds to the control of CU goes to the F1U CU, which again F1C DU, F1C DU connects it, and then you got similarly radio side of it, that is ENB side of it and GNB side of it, have a X1, X2, where the interface along with S1 for control. So that X2 is extended now for uh, enhanced GNB and the next generation ENB. So you got to support the um, coding, decoding, like example, you have turbo coding, and then you got polar coding for 5G. And so those are the coding aspects where CU has to deal with the um, processing, heavy processing, and then rest of it is management function, as you can say, bearer management, operation and administration, and then you got the GNB manager, then you got the radio manager, and then UE connection manager. So all these connect between the DU and the CU, and the RU is the one which manages the radio information. So 3GPP standard interfaces are available. Plus, you can see there are some application interfaces which need to be inside the DU and the CU respectively. And then you got the FFS, which is another interface for the small cell types. So you have got here functional interfaces, and this can be split. The example CU, UP, and CU, CP, that is a user plane and control plane for the central unit, can be split by using a even split. So each one can have independently, control signal can be sent separately, or packet flow for control plane is different, and same way for user plane it is different, and all of them can associate themselves with the respective GNBs or the ENBs which they are dealing with, whether it's a dual connectivity or whether it is a next generation GNB and upgraded ENB. So this is the product sheet which provides some of the compliances they have to do. Like 3GPP has got several standards. 15. This is I'm talking about a little bit older, but at least you get the idea that 3GPP has several releases. The 15 release dot 1.0 is for the OTA, and then 15.2.1 is for the mm, physical abstraction layer, which is also called converged layer. I believe CL and PL are same. So then you got the band support, what band you support, whether you're F1, FR1, FR2, whether you're in the millimeter wave or like N257, N78 is the most normal one, I believe, for 5G here. N78 and 79, these are the band which are referring to the carrier, and the spread sideband, what they have. The requirement for the aggregated for 5G is around 100 megahertz. For maximum 4G, it is 20 megahertz. So even by that itself, you will get 5 times the speed if you have the maximum 20 versus maximum minimum 100. So 5x is anyway you can achieve. So that's the kind of difference between the 4G and 5G. In practical terms, it depends on how you are pairing, whether you are pairing the 4G backend with the 5G new radio or 5G backend with the 5G radio. There is SA or NSA, and depending on the speed may have some bumps in the way. Then you got the formats for various support for carrier aggregation. And these are all based on the splits we'll come across later. You can have MIMO, you can have carrier spacing depending on how many, that is you can either have 15 kilohertz or 30 kilohertz, the resource blocks which are used for users to occupy in a time division duplex or in a frequency division duplex. Time division has got uplink and downlink different frequencies, whereas the what you call the TD, TDD, TDD uses the same band for uplink and downlink, whereas FDD uses different. So this is how you will have the MIMO, the carrier spacing neurology, and modulation. You got quadratic amplitude modulation, which can be 64 quad or 256 ohm. You have got core network options like ENDC for the option 3, 3A, 3X. These are all related to what stack you want to connect to between the two. Like, are you going to have a 4G stack uh, for the PDCP over the um, 5G stack with the SDAP. So how the stacks are configured, that determine the various options for the dual connectivity for the enhanced EU-tron network, they call it. And then you have got the LTE microwave aggregation, PDCP aggregation. So you got split bearer, and so these are the specification which provides various details. So typical example, I'll take a example of a Intel FlexRAN, how it is set up. So you can see here you've got the 5G radio here at the 28 gigahertz dynamic TDD, and so there are work going on in the XDD also. That means you can even TDD can adopt the FDD types, and so you can see that given a 5G millimeter wave radio, you can connect it to the 5G GNB, or you can connect it to the 4G LTE radio through TDD FDD for the 4G LTE baseband, and both of them are connected through X2 interface. And ENDC is the one which is S1U and S1AP, which connects to the EPC. In this case, it is showing EPC, so which means it is the 4G. So backend is this is the NSA implementation then, as you say, and the testing can be done for an application. And this, when they connect, you will find that 4G and 5G new radio can be tested. And this is a typical flex RAN, which is a product or a reference architecture provided by Intel. So we move on now to details of FlexRAN. So architecturally, FlexRAN is software modules with over the Intel. Of course, the FlexRAN being Intel reference architecture, it runs over x86 scalable CPUs and the networks and the accelerator option they provide. There is a library of all the uh, communications and other encryption, decryption, encoding, decoding, compression, all those, which is part of the FlexRAN SDK, which can be used for the RAN for the implementation of the 5G reference architecture, new for the new radio. They have the task controller which enables the tasks so that you can do parallel processing and all that. Then you have got the DPDK for the user plane, SRIOE and all those functions. So what you can see is that FlexRAN is a PHY application. This should be PHY. So it's a physical application which is done over the testing. You can see the physical application is here, and this is from older versions, but it is able to test the FlexRAN, which allows you to uh, wireless apply the wireless access for the new radio besides the LTE. So this is a test bed. When you want to create, you can use this as if you get the reference architecture, sign the document with Intel and get and run that. So you have got Intel FlexLab testbed, which is cloud enabled. You can also use the OpenStack controller to switch and put the VM, and then test equipment. You can connect, you can emulate, simulate, whatever you can do, create the necessary signals instead of doing it on the real, or you can do simulated, and then you can a front end, you have got the FPGA, which is able to do the FFT and IFT, and that is for fast Fourier transform for signal signal processing and all that. So these are either it is at the L1, you can have IQ samples, that is the quadrature amplitude. You have intermediate IQ samples which can be connected, and then that can be passed to the NIC, and NIC in turns can connect to the FlexRAN reference stack, which is software, and then it deals with the L2, L3 third party products and all that. And that's how you are able to do the cloud testing on this. So moving on, the signal processing, which I mentioned, there are many things which are there absolutely essential, like you have CRC decoding, encoding, turbo encoding. Like I said, example, I said polar coding for the 5G and all that. So pre-coding and mapping. There are many algorithms. All these algorithms are very they need to be implemented very fast. So most of them are implemented in either FPGAs or in the what do you call a way kind of a DSP types, and signal processing is very key for the optimization. And you can see that there are for achieving real-time performance with this, you understand that 1 millisecond is the requirement for a real-time application for 4G, whereas it is 0.25 millisecond or zero point 0.5, it's a variable one. So to achieve those, then you have to use all that single instruction multiple data, and then AVX512, that is the specific ISA instructions to be able to optimize. You have to do phase noise estimation, QR decompression, etc. So all this is possible using the SDK, because they have the API available for you to leverage. And so most of the real-time signal processing you can use FlexRAN. And this is Intel's. You also will have from NVIDIA another SDK, which is similar one, and they can also provide you the cool processing through GPU and the FPGAs, etc. So FlexRAN per cell you can pool, because when you do multiple cells, you bring the BBU with multiple cell being addressed through a single uh, DU, or it could be a D. So one DU can operate on say multiple radio heads and radio units. So how do you handle that? That means you are supporting multiple cells. If you are supporting multiple cells, how do you zero it down to the hypervisor and to the CPU, so that you can do a vCPU, so that you can do a what you call parallel tasking. So the FlexRAN software allows you the controller architecture, which provides the library to be able to do this multiple processing and within the real time, which is what we have put real time as. For 4G, the TTI is around um, 1 millisecond, whereas for 5G it is variable 0.25 to zero point 0.5. So these have to be met to be able to do a real-time processing, and especially it's which is closer to the lower down the stack, which is towards the physical layer. You have to process it with a uh, real time, and this is real time intelligent controller, we call them. So if you look at the application here, framework, you have got a this is the RAN application I'm talking of. So you got the core 1, core 2, core 3. You have got the scheduler, task schedulers, and you got the buffers for them. So various efficient architecture is to help the application to queue and then allocate the core and then execute within the real time, and then upon completion just generate the task dependency graph and all. Of course, task dependency graph is before schedule is generated, and then they are scheduled, and that is how the scheduler is able to provide the real-time uh, processing, so that you don't miss any calls and all that. So this is the internal detail, and you can get into more details, and graphs are drawn here to show that the architecture is able to meet, and similar charts you can get from other providers. So if you example, you take a SRIOV, which is single root IO virtualization, and if you get some processing to be fed through the receiver or the transmitter, because at the end of the day you have got the UE as a transmit for the upload to the tower, which is the receiver. And so what UE transmit is received by the cell tower, and um, uh, whatever transmitted by the cell tower goes to the UE. So you've got the uh, uplink and the downlink. And so uplink and downlink bandwidth have to satisfy those real-time requirement. The whatever the SIB or the reference signals are there and they are sent before the control is taken over by the network. This needs to be appropriately managed, including the attach, detach, uh, the creation of the bearer, creation of all those processes. So the SRIOE and DPDK help in this respect, and Titanium is one of the servers provided by one of the providers. And so Intel works with them to get you the kind of example. In this case, you can see 1, 2, 3, 4, 5 uh, 5 cells are being shown here. So uh, you can see the throughput is improved with parallel processing, so that you can get much higher, you can reduce the latency by almost 99.93. So you can see that instead of having a 15 microsecond and 20 microsecond, you are getting in 6 microsecond the processing, which helps build the real-time application, real-time operation over the V switch and all. And you can see that V switch is showing VFO, that is the virtual function, which is mapping the SRIOE through the VNFs and at the layer 1 and layer 2 in the V switch. And so the processing is very important. The latencies are important, and multiple cell processing, multi-threading, heterogeneous computing, all this is part of it. The split which I was mentioning to earlier, in the 15th, the release 15, the 3GPP functions were split. The CPRI is the common public radio interface. So from the radio, remote radio head, when it goes to the fiber, which is you use a CPRI, which is the common public radio interface. It's a very bulky, and so the backhaul takes it. So instead of that, the eCPRI is divided into eCPRI, so that you can get Ethernet. Can I call back, sir? I am in a recording. Thank you. Bye. So what happens is here we have uh, remote radio being split into. So RU, DU, and CU is the split, and eCPRI is the Ethernet. So instead of using the fiber optic frame, we can use the Ethernet frame to contain and send across. So it becomes easier for the interface RU to DU, and that's one of the major achievements here. And DU to CU, we have seen how the operation occurs. So this is the 3GPP functionality, the split, and there are n number of 8 bits are available. If I look at it, you got split at different low-fi, high-fi, low MAC, high MAC, low RLC, high RLC, PDCP, and RRC. Generally, PDCP is the packet data control protocol, where if you have out-of-sequence packages, they get reassembled. And obviously, remote radio controller is the one. Uh, radio resource controller is the one which provides the data, and then therefore you will find that CU should contain at least PDCP RLC, so you don't split at that layer. So normally the most popular one is 7.2, they call it, but put it 7. That means if RU is containing the radio frequency as well as low fi, then that's the one which is most optimum for RU. For the DU, anything that is not taken by CU and RU should be there. So both, you can use any of these options other than that 65432. 6 is being preferred by the that is micro cell folks. So there is a preference for the application. What applications you decide what split you should do. There is no single thing that will be the most important one. And so you can see that based on the splits, you can get optimization of the um, bit rates. Uh, Obviously, you can see the main thing. You can see 7.1, 7.2, 7.3 gets the optimum in this, in terms of the splits, how you do within the radio, and what functions you handle in radio versus what function you handle in central unit, and what you leave it to the distributed unit. So functional split is important, and this should be understood very well. and there is a split here showing for the low-fi and the hi-fi. 7 is split into 7.123, and you can see here the 7.1 is um, here on the side of what do you call uh, more towards the RF side, and 7.2 is somewhere in the antenna where you got symbols, antenna symbols are coming. The 7.1 is more towards the FFT and all that, so that it be better be in the RU side, closer to RU side, and then there is the low-fi and the hi-fi, and then you got the 7.3, which is only for downlink. So you can optimize depending on your use case, and then each provider chooses their own. Example, the preference for Geo in this case is split 6, but for Geo, for the Bhartiya, it is 7.2. So it depends on each one, and they can change also. There is no such thing that you have to use one. It also depends on the IPR and the various things that you hold, and obviously that's a, so functional split is uh, so now 5G can be deployed in enterprise also. It does not need to be into public by the service provider. It can also be in enterprise. If it is enterprise, it's a radio only, or so example in the A option A is just to use radio only, and that means what, the enterprise will only focus on radio, not worry about the data plane. B is it will worry about radio as well as data plane. C is it will take care of radio, data plane as well as control plane functions. Now, this can be either on-prem or it can be off-prem. Off-prem is in the sense that 5G as a service is a new service that is going to be public, becoming popular among the radio providers, among the telcos and Google, so the cloud providers, and that may be helpful for other enterprise to leverage them instead of bringing all of the work to themselves. So there are, it could be deployed and managed off the premise or on the premise. So choice is yours. So these are some of the deployment model for the enterprise. And coming to what the LMLC, that is the low mobility, uh, uh, low mobility and longer coverage. That includes the depends on how one handles. So there is one more equivalent of that. So if you look at this, normally our cell towers are say 30 meters kind of thing for the macro. And if you go for LMLC, then you may have to have a bigger tower with bigger with the same macro cell, or you can use super cell. Example, Facebook tried. You have 64 cells distribution with multiple antennas arrays and all that. If you do that, then your range may increase, and so instead of going for uh, few kilometer, you can go to tens and hundreds of kilometers. So basically you are increasing your range, and if you increase the range, there is a reference signal um, receive power, which is RSRP, and usually they are in the range of 80 dB millivolt to 1 minus 120, and so for LTE. So if you want to get the similar LTE types of coverage for a LMLC or a supercell, then what happens is you have to have this kind of a, so you can see a supercell, if you go to kilometer square, of course the coverage is omnidirectional in this case as shown. So super, if you have a supercell or if you have got the micro cell, then this is what the kilometer square coverage is there. If you get at the low end of it, low end means minus 120 dB is lowest and minus 120 dB is highest in this case. So near to far, as you go from near to far, your square uh, coverage more. So you can see here 30 kilometer square, what we can cover with the macro cell, 2,400 kilometer square can be covered by the supercell or even LNMLC, where somewhere in between. So you can see that supercell to macro cell ratio is around 65. So that means you can get 65x coverage, because all you are trying to do is to cater to the rural population, which is scattered and which is not like dense population like in urban. So that is what happens in this case. Uh, so This is one of the cases. And IMT 2020 approved three specs, out of which one was for the 5G RIT, another for the uh, 5G SRIT, and then the fourth one was the 5GI, which was for the telecommunication standard. This is something like ability to use the older technology of uh, encryption, decryption, and coding to be able to get a lower cost for the um, what do you call countries with a lesser amount of ARPUs. So which is fair enough. So that's what the low mobility large cell. So it means large cell, not large distance, but large cell. So large cell means what? If we when we looked at the cell, if the cell tower you raise and you try to get more coverage, 6x coverage versus 66x coverage. So basically coverage 1x is the normal macro. You can get 5x, you can get 10x, you can get 50x. So how much coverage you can do, you depend on how many antennas you can put together, and all this is empirical. It has to be estimated, and this work is well done by both Indian TSDSI along with the IITs and ISCs and all those CW, IT Center of Excellence for Wireless Information Technology. Kudos to them. They have done a good job, and we expect that this will be part of the 3GPP as understood by MTT 2020. So these are the references for you to go and look at it, and obviously this will help you in able to understand what I said. Maybe you can go through the previous uh, two videos, 2 or 3 videos which we had given under the Pandit Madan Mohan Malviya National Mission on training the teachers. If you goes through and follow this with this, then you will be able to appreciate the details that are brought here. And I think that is all I have. Otherwise, you can look at the glossary and all. And I think we can do in our learning management system all the questions, and you can put it in the RCM7 ramanujam.du.ac.in. Once this is filed into the uh, record, you will also have some question and answers which I will give so that you can complete those exercises to complete the course. And with that, I will close my session. Thank you very much.